Section 6. So here's your weekend task, calculating limits using the limit laws. So as we look at here's a list of limit laws. And so if we have two different functions and we're adding those two functions and we want to take the limit of that sum, then we can just add the limits of each function. So the limit of the sum, so the limit of the sum is the sum of the two limits. And while I'm taking the limits, the limit of a difference is the difference of the two limits. And then if I'm multiplying a constant by a function, so if I'm taking the limit of a constant times a function, well, I can just take the limit of the function and times that by the constant. And then when you're multiplying, if you're taking the limit of a product, then it's just the product of the two limits. So I can, basically I'm just separating everything. And then if I want to take the limit of a quotient, then I can take the quotient of the two limits, as long as my bottom limit doesn't equal 0. So those are the limit laws, 1, 2, 3, 4, and 5. So you'll use those in this section. So kind of get familiar with those. So basically any kind of addition. So if I'm taking, say, the limit as x goes to, say, 2 of x squared plus 2x, if I'm taking the limit of that, then I could just take the limit of x squared as x goes to 2, and then add the limit as of 2x as x goes to 2. Then it's multiplying 2 times x, so I could really separate that one. So this whole thing could be separated like this. 2 times the limit of x as x goes to 2. So you can separate using the limit laws. And then all you have to do on this one, I mean, you could probably even separate this one individually. You could even separate that because that's really just two functions. X times x is x squared, right? So you could even separate that one as the multiplication one. But now we can go ahead and just plug in 2 into our x squared. So 2 squared is 4, and then plug in 2 here, right? Because here I don't need to put in like 0.1 or 1.999 or 2.001 because I basically am not dividing by anything. I don't have a rational expression, so I can really just plug in these numbers. So when you have polynomials, it's really great to just plug them in. And so I get 2 here, and then 2 times 2 is 4, so I get 4 plus 4 is 8. So the limit of that is going to be 8 using the limit laws. All right, so here's an example for you. So don't get scared. So all we're going to do is basically find out so we can separate these, right? So the limit of a sum is the sum of the limits. So I'm going to find the limit of f of x, kind of like what we already did in the last section. And then this one would be plus 5 times the limit as x goes to -2. -2, that's not from the left. Let me fix that. X goes to -2 of g of x. So I'm going to do it just like we did in the last section. I'm going to find as I go from left and right of -2. So here's -2. As I go from the left, of -2 of f. So that's a big thing. I got to find f. F is here. So to the left and to the right, it's approaching the same number, value of 1. So this answer right here is 1. And then this function I'm looking at from the left of g, left and right of g, so that's approaching -1. And then I'm going to times that by 5. So then I get 1 plus -5 is -4. So this answer is -4. And then so I kind of do the same things. This one is separated to the limit as x goes to 1 of f of x times g of x, right? Because the limit of the product is the product of the two limits. Limit as x, and they always go to the same x value. G of x, so I'm going to find at 1, at 1 here. What is f of x going to? That is at 2, and g of x is at, oh, that limit doesn't exist, right? Because it goes from the right, it goes down to -1, but from the left, it goes to -2. So that does not exist. So I can't multiply a 2 by does not exist. So this one does not exist. And then f divided by g at +2. So here at +2, maybe I'll erase this for you. I'll be nice. So f on top. So this would be just the limit as x goes to 2 of f of x. And then divide that by the limit as x goes to 2 of g of x. So I need to find the limits as x goes to 2 of each of these functions. So at 2, it is f is 1.4, maybe 1.4-ish, estimating here. That's fine to estimate. And then g, the green one, is at 0. So there, I can't have g at 0, right? Because I can't divide by 0. So this one is undefined, or does not exist is fine as well. All right, so here are the other ones as well. So if we take the limit of a power, it's just taking the limit of the function raised to that power. So that's kind of like the power function. So we can rewrite that. So like for example, we did the one of, you could the 2 of x squared, right? So that could be rewritten as the limit as x goes to 2 of x, and then just square that, right? Because that power to that n is just some number. So then you plug in 2 squared is 4. It's the same thing. A limit of a constant, so the limit of a constant, so the limit as x goes to any number, really, 1 of a constant 2 is just going to be whatever that constant is. The limit as x goes to some number, say of 2, we'll just keep on throwing numbers out there, of x is just going to be whatever a is. So that's 2, because I just plug in 2 and I get 2. Here, where n is a positive integer, so limit as kind of same thing as 6 a little bit. This can be any function, so most likely if you had like an x plus 1 and that's being raised to the 4th, and you're taking the limit of that one as x goes to some a, then you can just take the limit of x plus 1 and then raise that to the 4th. Limit would be inside there. So this one maybe more explains x squared, but they both work. Of some x being raised to 5, then I can just really take 2 and just bring it to the 5th, and that'd be my answer. Here's 10. 10 is dealing with roots. Same kind of applies. These really are kind of the same thing, except for 10 is the same thing as 9, except for 9 to use 10. Maybe I'm sounding confusing. Whatever. But 10 is the same as 9, just with a fraction as an exponent. Really. Because any fraction as an exponent is the same as a root. So really, 10 is the same as 9, just we have a fraction as an exponent. And then 11, same kind of thing as 10, but maybe a bigger function would be inside there, like x squared minus 1. Maybe that's inside the root. And then so I can just take the limit of the inside and then root it to whatever number. So that's all the way. That's the kind of rest of them through 11. So here you go. Here's another example. So here we just expand that. I'm pretty sure this is probably going to 5. So this one would be 2 times the limit as x goes to 5. So sometimes this is kind of annoying just because you have to write the limit as x goes to 5 repeatedly of x, and you could say squared. You could even rewrite that squared minus 3 times the limit as x goes to 5 of x plus the limit as x goes to 5 of 4. So this one's a constant, right? So that's one of the limit laws. 7 through 11 or whatever is 4. This is just 5 times -3. This one is just, so you could rewrite this one as the 2 times the limit of, well, this one's just the 5 squared and then times by 2. Right, so 25 times 2 is 50, minus 15, 35, 35 plus 4, 39. If I'm doing my math right, I should, right, since I'm a math teacher. But sometimes I make mistakes too. It's okay. All right, this one, same kind of deal. I'm just going to break it apart, so I'm not going to do it because then that'll take up more. I'm already past 10 minutes, so you're probably already irritated with me. Okay, then there's direct substitution, which I've kind of already been doing anyways. So as long as we don't have a fraction, then we can just directly substitute in, plug in a into the x. That's what this means, right? So sometimes we try that first, which I've been doing. Like I said, polynomials are great because you can just plug it in here. When I plug that in here, I get divided by 0, right? So that's when we have to get close to, so then I have to do 1.001 and like 0.999, right? And then I have to evaluate those, kind of like what I've been doing with the last sections. So sometimes we can do direct substitution, right? And we don't have to use the limit laws at all. We can just do it. But here we could use the limit laws. This will be the limit as x goes to 1 of x squared minus 1 divided by the limit as x goes to 1 of x minus 1, and then you can expand this. You can keep on expanding it. So it'd be the limit as x goes to 1 of x, and you could do that being squared, goes to 1 minus the limit as x goes to 1 of 1, which we know is just 1, over same kind of thing here. So x goes to 1 of x minus the limit as x goes to 1 of 1, you know, it's just 1. And so here, again, we can't, even if I use the limit laws, I still, when I plug in 1, when I do direct substitution, I get 0, so I'm going to have to estimate and get close using these numbers. Okay, so evaluating this one. So if I plug in 0 again, I can't do that, so I got to get closer and closer and closer to that one. So I could get just closer and closer to that one, right? You know, negative point, 0001, and then maybe like 0.0001. But sometimes that gets annoying, so direct substitution would really be nice. So what I might want to do here is maybe just simplify the top. So then if a way I can simplify the top, so then maybe I can cancel these h's, right? If I could cancel those h's, then I wouldn't have to worry about dividing by 0. And so that sometimes is easier than like the last one when I said just plug in, you could just plug in these numbers. Sometimes in our calculator we might make mistakes, so it kind of takes longer. So it might be easier just to factor this top, FOIL this out, factor it, see if we can cancel those h's, and then we'll be done, right? So if we can rework this, so there's h, so I could FOIL that top out, right? So that'd be 9 plus 6h plus h squared minus 9, so those 9's would cancel out, right? All over h, and then I could simplify that. I could factor out an h and get 6 plus h. Now it's multiplication. Now I can cancel those. So this is what you really want to do in direct substitution, is factor, cancel out that denominator, so then you can just direct substitute. So now I can look at the limit as h goes to 0 of 6 plus h, which is very similar to this one. It's just I was able to cancel those factors. Now I can go ahead and plug in 0, and now I get 6. All right, so now it's a lot easier than plugging in those numbers of 0.0001 and running it through and then making sure the left side works, negative 0.9999, not negative 9.99, but negative, 0.110001, something like that. All right, so this is an easier direct substitution. So here's a little more complicated. So get used to this one, because you'll use this one a lot, even though we might not be taking the limits so often, but we'll use this technique that I'm about to use. So we used to like multiply by the conjugate on the bottom whenever we had something that looks like this square root minus something on top. Well, we're going to use it a lot in calc here in order to rationalize the top, because we want to rationalize the top in order to get factors. So once we have factors, then we can cancel out like factors on top and bottom, so that we can plug in these numbers so we don't get 0 on the bottom. So I kind of want to rationalize the top. So t squared, so I'm going to multiply top and bottom by t squared plus 9 minus or plus 3, the conjugate. And I'm going to do that on top and bottom, because now what's nice is with this is I don't have to actually FOIL the bottom, because I don't want to really FOIL the bottom because I want to keep it as product, right? Because once I have the products, then I can cancel something on top that's the same thing on bottom. But on top, I'm gonna have to FOIL that. But it's conjugates, right? So it's always just first times first, which a root times a root, same root. They're just gonna get what's on the inside, t squared plus 9, right? The roots are basically gonna cancel, and then minus 3 plus 3, because I don't have to worry about the middle, because those are gonna drop out. So minus 9, that cancels. Now I got t squared over t squared times square root of t squared plus 9 plus 3. Now I can go ahead and take the limit as t goes to 0. Video's kind of getting long, but it's the weekend, so you have time to watch this. Now it's multiplication, so now I can cancel this t, so I got 1 over square root of t squared plus 9, and plus 3 is on the outside. Now I can go ahead and direct substitute in that 0, because 0 squared is still 0. 0 plus 9 is 9. So I got square root of 9 plus 3, which is square root of 9 is 3. 3 plus 3 is 6, so I get 1/6. So there it simplifies out. But this technique of kind of rationalizing the top, whenever you see something like this top, you'll want to rationalize the top, because it'll kind of work out for you. And this is throughout calculus, these problems come up like that. So doing a lot of examples here, so hopefully you watch the whole video so you get all the examples. But we want to prove that this limit does not exist. So if I plug in 0, I get 0 over 0, but maybe I can simplify it and I can find the limit, right? So what I want to do here is just make sure that the limits show that the limit as x goes to 0 from the left of this, say, function f of x, we'll just call it f of x, we'll call this f of x, so I don't have to write it so many times, that these two, so if I can show that these two are different from each other, right, that this is something else, say, q, right, if these are two different things, then the limit doesn't exist, right, they have to be the same in order for the overall limit to exist. So if I come from the left side, so if I'm coming from the left side, that means I have a negative x value, right? So that means I have a negative x. So the limit as x goes to 0 of 0 from the left, the absolute value of x, or divided by x. So I got a negative, I would be plugging a negative number in here, so a negative x here, and this would be a negative x. Well, that absolute value is going to make it positive, right? So that's going to be some positive number. And this is going to be some negative number, right? Because it's a negative x. Well, positive divided by negative is going to be a negative. So that's going to be a negative some number. Now, if I come from the right, that means I'm plugging in an x that is positive, right? So I'm going to take a positive, and the absolute value of a positive is still positive. And my x down here is also going to be positive. So that's a positive. And then positive divided by positive, positive. So whatever, when I come from the left, my answer is going to be negative. When I come from the right, it's going to be positive. So those are not the same. So that means the overall limit does not exist. Okay, so this is where we start getting, maybe if we're not already, we're doing a little tricky here. So in order to prove like a limit exists, or maybe a limit doesn't exist like the last one, we might use the squeeze theorem, or called the sandwich theorem. Sandwich theorem. Okay, so this is saying that if I have two functions, and if I can find a third in between those two, so really actually what I'm trying to do is I'm actually trying to prove the limit of this one. And so if I find 2 on the outside of that, and I can find that these two limits, the limit of, as x goes to a of f of x, say if that equals L, and this function, the limit as x goes to that same a of h of x, that also equals L, that means that this function that's in between those two has to also equal L. So that's a that's something that you can use in order to prove that a limit exists. So maybe if you have a graph that here's the function that you're trying to find the limit of, right, some a value. So if you can find a function above and a function below that one, and then at this value, those two functions have the limit that's the same, that means this function in between, g, must also have that same limit. So here's an example that I can show you. So I need to prove that this function in between, I want to show the limit of that as x goes to 0 is 0. Okay, so that's my g function. So I need 2 on the outside of that, and something that's easy because this one's a hard limit to find. So we know that plane sine goes from, so we know sine of x goes from -1 -1 to 1, right? -1 to 1, right? It goes between there, our graph. So it goes up to negative, or up to +1, down to -1, right? Up to 1, down to -1. Correct? It just goes back and forth from. So then sine of 1 over x must also go from -1 to 1, because really I'm not multiplying by anything, right? So remember when we graphed, I'm not multiplying this by anything, so that means I'm still going to go from 1 to -1, nor am I adding anything at the end, so I'm still going to go from -1 to 1. So now I have sine of 1 over x goes from -1 to 1, so now I kind of have these functions out here defined. So I have to find those. So I need to come up with this middle equation, right? This middle function. Well, what do I need to do that? I need to multiply both sides by x squared, right? In here, so that means I need to multiply this by x squared and this by x squared. So that'd be -x squared is in between x squared sine 1 over x. This is x squared. So there are my two functions, right? A -x squared and an x squared. And I know what those look like. Here's, plain x squared. And here is -x squared. Right? So at 0, at the value of 0, I know what their limits are. I know what their y values are approaching. They're approaching 0. So if I have this different sine function in between, so sine functions in between, that's what I just proved here, that this function x squared times sine of 1 over x is in between these two, and I know the limit as x goes to 0 of a -x squared. I plug in 0, I can figure that out. That is 0. And then I know this one also, as the limit goes to 0 of plane x squared is also 0. That means this limit in between, by the squeeze theorem, or the sandwich theorem, x squared times sine of 1 over x has to also go to 0. The limit as x goes to 0 also has to go to 0. So that's how we prove that one.